that disappeared, which we'll see what happens. All right. So as we said, VA is 5 meters per second. We don't know what VA final is. And VB, it was stationary, wasn't it? That's 0. VB final is 4.8 meters per second. Calculate the speed of car A after the collision. There you go. Is everybody reasonably clear on how to do that? All right, it's just PI equals PF. And then MA, VA plus MB, VB equals MA, VA final plus MB, VB final. And then we know that's 0. So VA final, are they the same masses? No. VA final is MA, VA minus MB, VB final all over MA. All right, so it's just used elastic collision. Indicate the direction of the motion of car A after the collision. So if we see, like this one you can kind of do by logic, right? Well, actually if you did part A, you should get a positive or a negative value. If it was negative, that means it's going backwards. If it's positive, you go forward. Momentum must be conserved. So do you see if this is going 5 meters per second, then that means the momentum initial is equal to what, 1250 kilograms meters per second. Does that make sense? Okay. Then if we only look at VB final, right, the momentum of VB of this thing after the collision, because it's 200, so this is like 960 kilograms meters per second. So momentum must be conserved, right? So what has to be true about the momentum of cart A in general, in terms of its magnitude? Trini, what do you think? So what does momentum being conserved mean? Okay, did you say force or momentum? Okay, yes. So Trini helps us out by saying the amount of momentum it had initially has to equal the amount of momentum it has finally, right? The beginning has to equal the end. Does that make sense, Deborah?
Yes.
If that's true, right, Vivian, what has to be true about momentum of A? Okay, good. I mean, that's the hard way of saying it, but yes, she's saying that A has to add up to B to equal the original momentum. Okay, so that means what about the magnitude of A? Does it have to have some sign? Could this be negative? Could that be negative? Nelson, what do you think? Why? Okay, yeah, it's simple math, right? These two have to add up to be this. So you see how you can calculate it pretty easily. And that's what we're actually doing, see it? The momentum original equals the momentum of A plus the momentum of B. So all we're doing is taking the difference between these two and dividing it by the mass of A. And that will give us the velocity of A, final. And so we know that it's got to be to the right. Okay, if this was 1250 right here, if this was 1250, let's see, Lisa, what would be the velocity of A after the collision? Oh, yeah, so if the total momentum of B was equal to the initial total momentum of A, what would be the velocity of A after the collision? Kyle, help her out. What has to be true about the momentum before and after the collision?
They have to stay the same.
The total momentum has to be equal. So if the momentum of B is 1250, what must be the momentum of A? Okay, don't look at the 960. What I'm saying is, if this is 1250, and this is the original of 1250, then what must this be? Yeah, that must be 0. And that would be one of those things where it's like, boom. And have you seen those balls on the strings? You pull one, it goes. Like that is this. All of the masses are identical, and the balls are very, very hard. They're very rigid. They're steel. And because they're ball bearings, which have a high rigidity, then the time it takes to collide is really small. And if the time it takes to collide is really small, then it approaches a perfectly elastic collision. And perfectly elastic collisions mean I just give you my momentum. And because all the masses are the same, when you drop one, bam, it knocks the other one off the other end. Bam, 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 and they just bounce back and forth. Right? And it's fun, and it goes on for a long time. The better it is, the more it goes on for. If the strings are a little bit off, then it dies quick. Yeah, that sort of stuff. Okay, anyways. Is this an elastic collision? What would you say? Well, they tell you this. Yeah, I would say, yeah, I would say it's elastic. Let's see. I mean, there's no such thing as a perfectly elastic collision. So it's possible that some of the energy is lost, but in general, that it's an elastic collision. Let's see what it says. Okay, so yeah, our answer, no, that's not it. What is this? Was it 2008?
Yeah.
What's that? Oh, that's cushion 2. Okay, we did part A already. Part B, 1.2, just conservation. Then for the second part, yeah, the direction to the right, so that's fine. And part C, it's not elastic. Oh, okay. All right, you know the part, or what I just said about how, oops. You know what I just said about how, yeah, it's kind of like it's not a perfectly elastic collision. In general, it's elastic. What they want is, how would you prove to someone that it's an elastic collision or not? Like, how do you show that something's elastic? What balances? Let's see, Kevin, how do you know something's perfectly elastic? This bounced, but it's not elastic. Think of the definition of elastic collision. What are the 2 criteria that have to be true? Well, what's one thing that has to be true for any collision? Trini talked about it earlier. What's that? What must be equal? Okay, so you can just say momentum is conserved, right? All right. Alvin, what's the second thing?
Kinetic energy must be conserved.
Yeah, kinetic energy must be conserved. So if they say, is this elastic? Well, we look at it and we say, well, it's reasonably elastic. They're kind of like asking, is this perfectly elastic? So how do you prove that? Just compare the kinetic energy. So just write out, so just compare. Do like, I don't know, if you want KE final minus KE initial. So do delta KE. If delta KE equals 0, you know it's elastic. If delta KE is not 0, then you know it was inelastic to a certain degree. That's all you have to do. Well, it's not that it's inelastic. You just know that it's not perfectly elastic. So if you look at that and you're like, well, wait a minute, they bounce off each other. According to your definition, that should be elastic. True, but they're really asking, is it perfectly elastic? And the answer is no, because this is going to be off by a little bit. And then the justify, all you have to do is that. All you have to do is say, to justify, all you have to do is say, delta KE should be 0 for an elastic collision. All right, questions on the first one? All right, what's the next problem? 2009 B or BB?
B.
Oh, sorry, 2009 B. Okay. Is that right? Is it this? Okay. All right. So this says, derive the equation P equals this, and that relates P and M. Period is the time it takes to go around. Time for a revolution. Okay. And we know that in order to get a time for any object to move, like if we look at this, this has to have some velocity v, and that velocity v is what's keeping this up. So we can do something like, we do the force diagram on this. There's this puck going like this, that's tension. Then there's this mass on the bottom like this, and we see the tension is mass times gravity, m2 times g. Does this make sense? This puck is swinging around like this out of the board. And then that puck is keeping this little guy up in the air. Okay? So now we just say, all right, what is the only force acting on this? The sum of the forces on this puck in the x is mv squared over r. So that means T equals mv squared over r. Over here, T is mg, so we get m2g equals m1v squared over r. All right, so that allows us to say the velocity of that puck, v is the square root of m2gr over m1. So that gives us the velocity of the puck. That's not the time, that's just the velocity. Why did I do that? Because I don't know what else to do. I just know that if I do a force diagram, this is what it gives me. Now the question is, how do I connect velocity with time? How do I connect velocity with time? Tiffany. Yes, what formula connects velocity and time? Okay, you could use that. We don't necessarily know the acceleration because the acceleration tangent to the circle, we don't know that. Oh, there isn't an acceleration. Well, yeah, there's no acceleration tangent. So in the simplest of terms, okay, Tiffany's answer was true, but in the simplest of terms, what connects V and T? Genuine? What's the easiest equation you can think of that has a V and a T in it? Not sure. Helen, can you help her out? Okay, that's what Tiffany said. Wow. Can anybody think of anything simpler than that? Mr. Brito? X equals VXT. Or V is X over T. Right? I mean, I think that's simpler, but I don't know. It's up to you. But anyways, I don't want to beat a dead horse. But yeah, the point is, you take this. Do you see what we're doing? Yeah, it's just distance over time. So what we're going to be doing here is just that. This is equal to that. And so if you want T, T is equal to the square root. And what is the distance that that puck travels? The X? Yeah, did you see it's 2 pi r? So it's 2 pi r over the square root of M2GR over M1. And you see we just proved it. Or we just derived that. Because this is that. Questions?
Am I supposed to go pay today?
Nah, just go around and put away all the cart stuff and then take the aluminum things and put them back over there against the wall,
Alright.
the tracks. Questions? All right, well, I'm gonna take you at your word and we're gonna move on. All right, so this looks like the second part of this problem. Okay, so they did this experiment where they spun it around and then they measured 4 masses. So they're trying to find the value for G. So what quantity should be graphed to yield a straight line with a slope that can be used to determine G? So this is that thing again that I mentioned that's about fractions. So what did we do? We just said that the period was equal to 2 pi r times the square root of, gosh, was it like m, I can't remember. It's up there. What is it? You have it in front of you, don't you? What is it? Say again? 2 pi square root of m1 r m2g. Okay, so we want to create a graph that's going to give us G. So what we can do is isolate this for G and see what we get. So if we do that, we should get something like, gosh, if we move this, oh, go away. Go away. Go away. What is this? What the fudge? Close, 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 close. It's like it's there, but it's not. What the fudge? All right, yeah, so we can put this under here at 2 pi, then square both sides, and then you can put it like this. So you could say G is M1R over M2 times P squared over P over 2 pi squared. So if you do that, you get G is equal to M1R over, M1R 4 pi squared over M2 times P squared. Okay, R is a constant, M is a constant. So what quantities should be graphed to yield a straight line? Just looks like, because that's a constant, that's a constant, that's a constant. Oh, we can't do that because we have those two things together. Let's take a look and see what they did.
That's 2008.
That's the wrong one. Oh, I gotta go get it. Oy. This is 2009B, right?
Yeah.
Whatever. Oh, okay. Ah, that's slick. All right, so when we looked at this, we came up with this crazy sort of thing that was like G is equal to a bunch of stuff, right? There was like R and M1 and 4 pi squared, and then on the bottom was M2 and P squared, right? So the problem is, how do you make a graph with this, right? You can't graph, like, if you do the graph, there has to be something on top and something on the bottom. It's like G, if you want G to be the slope of the graph, then you have to have rise over run. Does that make sense? And how do you do that here? Well, what they did was this sneaky thing where they said the rise, if I put 1 over P here and I put M2 there, then I can get a slope that's this, or a slope that's this times a factor. So I'll show you what they mean here. So see, they took 1 over P squared, and then they took M2. M2 is the obvious choice, but then the 1 over P squared, that's sneaky. That's a little tricky. And then you just put it on the graph. So once again, how to deal with this. So if you get something, like their thing was G is equal to some blah, blah, blah stuff, and M2 and P squared like this. And if you want to make a graph that gives you G by the slope, because you're always looking for this to be the slope of the line. So that means in order for G to be the slope of the line, you need something on top and something on the bottom. So if I do 1 over P squared for the top and M2 for the bottom, that allows me to come up with a line that will have the slope that I'm looking for. And so then here you do 1 over P squared, and then you have the M2 there. So then, and of course this is just rise, this is run, so when you graph it, everything will work out. Now, when you graph, make sure that you do some things. Make sure your graph takes up as much of the document, of as much of the space as you can. You don't always have to start from 0, 0, unless you want to. Make sure that you label with units on both axes. Okay, and make sure you know what kind of graph you're looking for. If you're looking for the slope of this line, then this line should be what? Like, how is it? Like a quadratic? Is it a curve? Is it a straight line? You see, it has to be a straight line if you're looking for that slope. Sometimes if you take the data points from an experiment and graph them, like if you're kind of looking for the behavior of a bunch of dots, that often comes out to be a curve. But when they tell you to show a value from an equation, that usually comes out to be a line, because you're trying to manipulate the equation to get a ratio so that you can get a slope. So make sure it's big. Make sure that you label. Also, make sure that you use, like if your dots are like this, if they don't make a straight line, make sure your line is best fit. Anytime you're looking for a specific slope, you have to use a best fit line. Okay, so you put your dots. Okay, so your dots are from the data. This is a best fit line. And then if you do any calculations from this, watch out, well, you know, I'm just going to leave it there. So label, use the whole space, make a best fit line. As we can see, if we go back, if we go to the rubric, they'll say labeling both axes, scaling both axes, reasonably correct plotting, and then reasonably correct best fit line. Right? That graph is worth 4 points. Even if you like do the graph wrong, you can still get the points. like if your data's wrong and it makes your graph wrong, you still get 4 points. As long as you label everything, use the whole graph, and then do all that stuff. All right, so then for the next part, they're asking, use your graph to calculate the experimental value of G. So in this one, you know, G, if we graphed 1 over p squared over m2, right? Sorry, that's not G. The slope of our line should be 1 over p squared over m2. Okay, what do we need to do to this to get, well, first of all, how do you find the slope of this? Okay, let me say this very clearly. Don't use data points. Do not use data points to find the slope unless those data points are specifically on the line. Okay, let me see if I can communicate what I'm saying here. If my data points are here, 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 and there, and so I do a best fit line like this, I can only use one of those data points. Do you see that? If you use these 2 data points, you're going to get the slope of that line. What the fuck? Yeah. You're not going to get the slope of the line that you graphed. You must pick points on the line, and I recommend that you pick easy points on the line. Then you have to show delta y, delta x, and then get your slope. Okay, so with graphs, several points. Number 1, label the axes with the appropriate values. Number 2, use the space. Okay, and number 3, make sure your best fit line is like in between most of your values. Then number 4, when you find the slope, use the line. Don't use the data points unless the data point is exactly on the line, then you could. All right, so if I do that, then my slope is going to be 1 over p squared over m2. How do I convert this slope? So that's some number. How do I convert that number into G? Well, if you go back to the equation that we had above, it was something like G is equal to, I think it was M2, no, not M2. It was like M1 R 4 pi squared over M2 p squared. Remember that? So then all you have to do is just multiply. G should equal the slope times M1 R 4 pi squared. Right, you see that? All you have to do is take G and multiply by that slope, and you're good. And then we can see that here. Oh, I had it flipped. Sorry. But whatever. Multiply it by the constant that you got from the original equation. So just take, oh no, I was right. Ha ha ha, cool. So just take the slope, multiply it by whatever that gibberish was that you that like completes that formula, and then you'll get your answer. All right, questions on that one? Okay, important topics to take away from that is that graphs can be free points for you if you stay consistent and remember those 4 things about the graphs. Label the axes, scale the axes, do your points, thank you. Do a reasonable best fit line of those points, and then whenever if you have to find the slope of that, make sure you use the dots on the graph. Okay, so what's the next problem? 2010 Form B. Okay. Question 2, did you say? Oh, 1 and 2. Oh, okay, cool. Okay, yeah, we should be able to do this now. Calculate the speed of the block when it leaves the track at point C. So that, you're just going to do some, whatever, PEI equals KE final. Let me see, does it have an initial velocity? Released from rest, okay. Negligible friction, so goes around the loop, comes back, goes off there. Oh, and you have to, it depends on how you do this, right? Because this kind of also has a PE final, right, from here to here. But if you go like this and use H as 1.5 meters, then you don't have to worry about that one. You see what I'm saying there? Since this is 0.5 meters above the ground, if you go ahead and say, I'm just going to use this height right there for my PEI, then you're good. Okay, so next, on the figure below, draw and label the forces. That notice when it says not components, that means don't crack vectors. Just draw the base forces. That act on the block when it's at the top of the loop. So right here, what forces should I have? Give me one of the forces, Jenny.
Gravity.
Gravity. Boom. F sub G. Okay. Then Michelle, give me another force. What's that?
The up one.
The up one. What's the up one called? Okay, so I'm going to assume that you, well, your answer's right, because it is Fn. But in this case, does it actually point up?
No.
Yeah, good. Right, do we see that Fn in this case actually points down? Okay, but I love that you nailed that. That's great. Because it is the normal force. Remember there was 4 things that make things move in a circle? I mean, there's more than that, but we just concentrated on tension, gravity, friction, and normal force. So there you go. That's great. Calculate the minimum speed the block can have at point B without losing contact with the track. Well, it says calculate. I don't know. If you were just slick and you remembered that the minimum vertical velocity is VRG, equals square root of RG, that'd be pretty funny. But how do you get that, right? You use the force diagram. Because what are the sum of the forces on that thing? Oh, what? Anything in the universe that moves in a circle, the sum of the forces is what? mv squared over r. So you know you're going to get Fn plus mg equals mv squared over r. Okay, and you remember, well, I don't know if I did this in here. If I take this yo-yo and I spin it at the minimum velocity, what's the tension in the string right there? There.
0, 0.
Yeah, you see how it's 0? So like, does it make sense to you that I can spin this at barely the speed that even though that string is straight up, there's no tension in the string because it's basically falling through the top of that spin. Okay, so that means that at the minimum vertical velocity, the only force pulling down is gravity. So at minimum vertical velocity, Fn is 0. And that's the key. This goes away, V is square root of RG. Okay, then for D, calculate the minimum height above the bottom of the track at which the block can be released, and it will go through the loop without losing contact with the track. So we just determined that the minimum velocity here was what? Square root of RG, right? So what is the total energies at this point? Van, what's the total energies here? What 2 types of energies does it have? What's that? If you are in a cart on the top of that right there, what types of energy do you have? And you're moving that way. You don't know? I think you're overthinking it. Think of the types of energies that we've studied. And I just said you are moving. What's that? So what type of energy do you have? You do have momentum because you have a velocity. What type of energy does any object that has a velocity have? What? Yes, kinetic. So you have KE. Also, would you like to be at that place if it stopped? Why not? Now you're going to fall. And if you're going to fall, you have what type of energy? What's that? Yes, potential. Okay, so you need to just like throw out what's on your mind. Because like, and I think this is happening to a lot of you. You're thinking too much. Like you think about every word that comes out of your mouth and you're not sure. So then you don't say anything and therefore you don't answer. It's the same reason why I don't give any points for homework that doesn't have something on everything. You are used, like it's like you have to have the right answer. And so if you can't answer correctly, you don't want to give an answer. Well, the problem is that means you don't give an answer, which means you get no points. See, so I'm trying to force you to give answers like on the homework so that you'll get the points. That's the idea. So stop filtering yourself and just throw out what you think. Okay, anyways. I've never made fun of someone for giving an answer, so at least I don't think so.
Unless it's ridiculous.
Yeah, well, unless it's people that I know. Like if you said the wrong answer, I might make fun of you. No, I'm just kidding. I'm not going to do that. Anyways, if he gave me the wrong answer, for sure I'm making fun of him. So does this make sense to everyone here, that you have these two types of energies? Well, this, you only have PEG initial, right? So what we're looking for is, I think they said, what is the minimum height above the bottom of the track? So they're looking for this H. We don't know what that is. It's not 2 meters. They're looking for this H that will help you get there, okay? If you wanted to, you could do something like this and say this PEG is like mg h minus 1.2 meters. If you wanted to. You could just do it in one shot. And so then you would just set that, so you would say mg h minus 1.2 meters, and then that has to be equal to ke final, or, oops, instead of ke final, we could say 1/2 mv final squared. Those masses cancel, and so then I get, oh, I'm looking for h, so yeah, I gotta factor it out, blah, blah, blah. So I get h is equal to vf squared over 2 minus, plus 1.2 g over g.
I think the other way was
Is that right? I think that's the right algebra. Yeah, so whatever it comes out to be. But you get the idea. Just set these two energies equal to each other. But the trick, the thing they're trying to find out if you know, is that this has to have a minimum velocity. And that minimum velocity, whoops, I forgot to put that in. That minimum, it's not that I forgot, but this becomes RG, right? Because the minimum velocity is square root of RG. So when you put it in, that gets squared. And you can cancel out G's. Oh, look at that, that's fun. So it's RG plus 1.2 G over G. That cancels, and you get R, which is 0.6, so this becomes 1.8 meters. So if this had said 1.8 meters, then it would have just barely gone through that circle. Like right at the top, you'd be almost stopped. And then, not exactly almost stopped, but you'd feel like you're weightless. Because the only thing affecting you would be gravity. You wouldn't be almost stopped. You'd have a velocity of square root of RG, but you'd feel like you were weightless because the only thing affecting you is gravity. All right, so there's that one.
So fly landed on it, keep fall.
What's that?
So fly landed on it, give more mass, you'd fall.
Oh, nah, the mass doesn't matter. What would happen when you're falling with the acceleration of gravity, it just means like if you were at the very top of that loop and you had a pen in your hand and you let go, it would float in front of you. But then once the track starts pushing you in a circle, it hits you in the face. So don't do that. Okay, we move on. Number 2, did I say?
Yes.
Okay, number 2. The simple pendulum and a bob hanging from a light string, blah, 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 blah. Frequency, frequency.
Yes.
Never mind. Meh.
Whoa.
Oh, never mind. I confused this with another problem from years before, where there was a pendulum inside a car. So I think I saw the pendulum and I thought it'd be the pendulum inside that roller coaster car. And then you have to like judge the forces. So we haven't done frequency yet. So that's fine. Okay. So let me see.